Hello everyone! Recently the media has been constantly talking about so-called rare earth metals, and about how some countries would like to gain access to them. But in reality, if you read this book, it becomes clear that even now, rare earth metals are becoming the new oil, meaning they are a strategic resource that can lead to new conflicts. So, what are these metals and why are they so important? Well, let's figure it out. Since ancient times, people have been driven by the struggle for resources, which include various metals. Until the mid-20th century, the main strategic metals used in industry were iron, copper, nickel, and manganese. However, now since the 1970s, technological progress has started to develop at an exponential rate, which led industries to need new metals and materials that had not been used before. The new types of materials became new ceramics, glass, and semiconductors, as well as various alloys. And all of them consisted of a whole soup of various substances, the properties of which were significantly improved by the addition of rare earth metal compounds. For example, adding a small amount of lanthanum oxide to glass. It significantly improves its resistance to alkalis. And a small addition of Dysprosium and Europium compounds to strontium aluminate creates some of the most effective phosphors with long afterglow. But to make it clearer for you, let's take a look at the periodic table of chemical elements as a whole. And here we will find those very rare earth metals. Yes, here they are. 17 metals that make up the bottom row of the so-called lanthanides, named after the metal lanthanum. And also a couple of somewhat standalone ones, Yttrium and Scandium. These metals will soon play a key role in energy and in the transmission of information around the world. Not without reason, in 2022, the US Geological Survey included all rare earth metals in the list of so-called strategic elements, on which the power of this country will depend. Paradoxically, if you look at the abundance table of elements in the Earth's crust, you'll see that the abundance of rare earths is not much lower than that of tin and slightly higher than that of mercury. But why are these metals called rare earth metals? The thing is, rare earth metal deposits are often very scattered, meaning they are far apart from each other. For example, let's take a look at this map, which shows the main reserves of rare earths around the world. As you can see, significant deposits of rare earth metals are found in only a few parts of the world, and commercially, it's not always profitable to extract them. However, in minerals like monazite or gadolinite, rare earths occur together. So, if you're lucky enough to find deposits of these minerals, you can extract almost all the rare earth metals from them. Yes, it all seems simple in words, no? However, due to their similar chemical properties, separating some metals from each other can sometimes be an extremely challenging task. It's not without reason. The rarest rare earth metal, lutetium, was only discovered in 1906, and in its pure form. It was obtained only 47 years later, after humanity had already tested the first hydrogen bomb. But still, aside from the rarest rare earth metal, let's briefly go through all the others to understand where these metals are used and why their value will only increase in the future. Let's start with scandium, which is a relatively light metal with a slightly yellowish tint. In nature, like many other rare earth elements, scandium is found in minerals such as gadolinite or thoisoi. However, there are very few places in the world where these minerals are found in concentrated form, which is why scandium is often extracted as a byproduct of uranium or iron mining. Because of this, the price of scandium is the highest among all rare earth metals, at about 40 euros per gram. To obtain metallic scandium first, its oxide is mixed with hydrofluoric acid, and then it is reduced with metallic calcium to get the metal. So that's basically how almost all rare earth metals are obtained. Like other rare earth metals today, scandium is used exclusively as an additive. For example, aluminum alloys with the addition of scandium become much stronger. Scandium makes them much stronger. Pure aluminum with fine grains and crystals is less prone to fatigue and cracking. Alloys make fuselages and sports gear. From such alloys, today they make fuselages for fighter jets, as well as some sports equipment. But I think you know, for some countries today, having reserves of scandium is a priority, as fighter jets are likely more important to the country than lightweight sports equipment. Next after scandium is yttrium, which is already a shiny metal, like scandium, which oxidizes weakly in air. However, unlike scandium, the price of yttrium is much lower due to its higher abundance in the Earth's crust and the simpler extraction process from ores. Because of this, today many types of yttrium aluminum garnets are made from yttrium and aluminum oxides, which are widely used in solid-state lasers that are commonly applied in medicine. In addition, if yttrium oxide is mixed with nitric acid, copper nitrate, barium nitrate, and citric acid, then when heated strongly, such a mixture forms a black powder for the synthesis of high-temperature superconducting ceramics, which is quite cheap for the transition to a superconducting state. Liquid nitrogen. Instead of the very expensive liquid gel that was previously required for low-temperature superconductors. Such ceramics will help create cheaper magnetic levitation trains in the future. After all, superconducting wires are already being developed that can handle huge currents, which allows for the creation of super powerful and inexpensive magnets capable of supporting massive weights in the air thanks to the magnetic field. After yttrium, we move on to the so-called lanthanide series, which logically starts with the metal lanthanum. This metal, like all 7 that follow, has a much higher chemical activity, as it is located closer to the alkali metals in the periodic table. To make it clearer, I'll show you how the periodic table of elements should actually look in its extended form, since often the lanthanides and actinides are placed down below. Yes, it's clearly visible now. That lanthanum is closer to the active alkaline earth metals, which is why it has similar chemical properties. Closer to barium, lanthanum oxidizes very quickly in the air, so it's better to store it in an argon atmosphere or in mineral oil. Lanthanum reacts very actively with hydrofluoric acid, forming lanthanum fluoride, which is currently used to create special glass. Z-blend, from which most of the optical fibers for creating high-speed internet are made today. In addition, due to its high chemical activity, lanthanum is used in its metallic form as part of ferrocerium, or simply the flint found in lighters, which produces burning sparks when rubbed against a wheel. Here, lanthanum helps with the self-ignition of metals, along with cerium. By the way, about cerium. This metal, like lanthanum, is very chemically active, which is why it doesn't store well in the air, eventually turning into a dust of dioxide. Cerium. By the way, this slideshow makes it very clear. How do rare earth metals store in the air? It's noticeable that along with lanthanum, cerium is on the list of the most active metals, which is why these metals are better stored in ampules in an inert atmosphere. Cerium is obtained from one of the most common minerals for extracting rare earth elements, monazite. This mineral, by the way, is known for its increased radioactivity due to the compounds it contains. Thorium is the most common radioactive metal on Earth. Interestingly, thorium and its compounds are rarely used today due to people's concerns about its radioactivity. Moreover, thorium has already been replaced by safer rare earth metals. Because of this, especially in China, huge mountains of technical thorium oxide have formed, which is a byproduct of rare earth metal production and is of no use to anyone. In China, of course, they try to downplay this, but rare earths continue to be mined. But let's get back to the goal. Due to its high abundance, this metal was the first rare earth metal to be discovered. Moreover, its oxide is the easiest to extract from monazite due to a different oxidation state, which distinguishes it from other lanthanides. The cerium oxide obtained today is used along with yttrium oxide to create unusual incandescent filaments that can convert thermal energy, gas, combustion into light. This effect is also called candoluminescence. And the oxides of rare earth metals are very effective in this regard, because of the unusual structure of its electron shell. After cerium, the table lists praseodymium and neodymium, which are the most important metals today for producing powerful neodymium magnets. The thing is, one of the most magnetically dense compounds today is the compound of neodymium, iron, and boron, which is now commonly referred to as an intermetallic compound. That is, it's not an alloy, but rather a specific compound of metals with boron. As a rule, intermetallics are very brittle, which you can test by accidentally bringing together a couple of powerful neodymium magnets or hitting them with a hammer. From a strong impact, such a magnet easily crumbles and creates sparks, just like neodymium. The intermetallic compound contains a fairly active metal. If you dissolve such a crumbled magnet in acid, and then add oxalic acid to the solution, theoretically, you can extract pure neodymium oxalate from that magnet. unlike other rare earth metals, whose compounds are often white. Neodymium compounds are purple in color, so it will be fairly easy to distinguish neodymium from other metals by color. If you heat the resulting oxalate from the dissolved magnet, it will decompose into an oxide, and you can confirm that neodymium is indeed used in the magnet, since the powder should change its color to pink. However, upon heating, it becomes clear that, in addition to neodymium, some other metal is also used in these magnets today. The color has changed to some dark brown. After a little searching, I found that in modern magnets, praseodymium is also added to neodymium, since its oxide has just such a dark brown color. Besides being a cheaper option, praseodymium, like other rare earth metals, is added to neodymium to improve the corrosion resistance of these magnets, as well as to enhance their demagnetization resistance. As you can see, today many industries depend on such. These are the magnets that are at the heart of wind turbines or engines in electric vehicles. In fact, 95% of all revenue generated from the mining and production of rare earth metals comes from the industry that produces those very permanent neodymium magnets. And I think it's no secret that in the coming years, the industry of powerful neodymium-praseodymium magnets will only continue to grow, and so will the economies of the countries that control the extraction of these rare earth metals. Praseodymium itself, which is added to those magnets, is very similar to neodymium in its chemical properties, although it's a bit cheaper than neodymium. The only thing that characterizes and distinguishes praseodymium from neodymium is the green color of its compounds, unlike the pink-purple shades of neodymium. In addition to neodymium and praseodymium, sometimes another metal, samarium, is added to those powerful magnets, which I find hard to still call neodymium magnets, to enhance their magnetic properties. Samarium itself, along with neodymium and dysprosium, also has high chemical activity, which is why it is stored in a vial in an argon atmosphere. If you combine this metal with cobalt, you can create quite powerful samarium-cobalt magnets that can withstand temperatures up to 700 degrees Celsius without losing their magnetism. In comparison, those neodymium-praseodymium magnets can lose their magnetism at just 110 degrees Celsius. So samaria is also very important today in the production of high-temperature magnets. They are also often used in industry as well as in the military, after neodymium, praseodymium, and samarium. In the periodic table, there is europium, which is quite different from its rare earth counterparts in terms of chemical properties. Unlike samarium, which barely reacts even with acetic acid, europium does react with regular water. It's as if this isn't a rare earth metal, but some kind of alkaline earth metal. After the reaction with water, the resulting europium hydroxide can be calcined to obtain its oxide, which is the main raw material for europium compounds. At first glance, europium oxide appears to be a white substance, but if you turn on an ultraviolet light, the europium oxide immediately shines with a red color. About 30 years ago, europium compounds were often used to create phosphors in old televisions that could glow red, from the impact on them, electrons from the electron gun of the television. But now, compounds of this element are mainly used in QLED displays, which are capable of transmitting the tiniest shades of color, in the latest screens with quantum dots. In addition, if you add just 0.5% of europium compounds to strontium aluminate, it will immediately shine with a green light under ultraviolet rays, creating a phosphor with quite a long afterglow. By the way, they are now applied to many watch hands, and they are also used to make light storage devices. So europium is also quite an important metal right now. After europium comes a rather unusual metal, gadolinium, which has some unique magnetic properties. First of all, unlike europium, gadolinium is quite stable in the air, which allows it to be stored without degradation, just in the form of such a cube. In addition to that, gadolinium is very strongly magnetic, as it is the strongest paramagnetic material among all the rare earth metals. Because of these unusual properties, gadolinium compounds are now used as a contrast agent in MRI, commercially known as Magnevist. After gadolinium comes terbium, which, like other metals from the lanthanide series, is just a piece of metal, which any passerby could just kick. However, knowing the value of this element and its applications, he would hardly do that. If you dissolve a piece of terbium in any of the common acids, you can obtain a compound of this metal, as for example in hydrochloric or sulfuric acid, this metal dissolves quite well. Along with europium, Terbium compounds also glow under ultraviolet light, but they emit a green light instead. For example, when you add a compound of this metal to the glass composition, the so-called terbium glass starts to glow with a bright green light under ultraviolet rays, just like uranium glass. However, unlike uranium glass, terbium glass is not radioactive. So, now this metal is added not only to the glass composition, but also as an additive to various garnets that are used today in solid-state lasers. After terbium, in the periodic table comes dysprosium. The unusual property of this metal is that its paramagnetic properties can change depending on low temperatures. To demonstrate this effect, I decided to conduct an unusual experiment. In it, I built a special stand where dysprosium will change its magnetic properties when cooled with liquid nitrogen. To do this, I placed a piece of dysprosium in a dish, and then I poured a little liquid nitrogen into it. After a few seconds, the nitrogen stopped boiling. This means that the dysprosium has already cooled down to the temperature of liquid nitrogen. Therefore, as soon as I bring the cooled dysprosi close to the magnet, it is immediately attracted to it, resting against the hard surface of the glass. This is because at temperatures below 88 Kelvin or minus 185 degrees Celsius, dysprosi acquires ferromagnetic properties, which is why it can already be attracted to a magnet from above, since it has stronger magnetic properties than at room temperature. If you blow on this metal with a hairdryer, it will warm up a bit, causing it to stop being a ferromagnet and fall back into the liquid nitrogen. So, this cycle can be repeated endlessly, or until all the nitrogen in the lower dish evaporates. In addition, if you alloy dysprosium with iron and terbium, you can create a very unusual alloy, terphenyl D, which can change its size under the influence of a magnetic field. In this way, you can create unusual vibration speakers that make the entire surface beneath them a source of sound. Next on the table is the unusual metal holmium, which, like the previous dysprosium, is quite stable in air. However, right now the tech sector is more interested in the compounds of this metal rather than its metallic form. Interestingly, for example, holmium nitrate can change its color just from different lighting. For example, in LED light it appears yellow, while under fluorescent light it looks pink. It's all because of the unusual electronic shell of this metal. By the way, recently scientists from IBM started using it for storing information in quantum computers. Imagine, one atom of holmium can store an entire bit of information. If you do some calculations using artificial intelligence, you can store this much on 1 gram of holmium. That's so many gigabytes that it roughly equals the volume of 23 million hard drives, each with 20 terabytes, which is just an unimaginable comparison. So I think, what, in the future? Will everyone store all their photos and videos from their entire life? Just a few micrograms of holmium. Next to holmium is the metal, erbium, which is now important in medicine. The thing is, the compounds of this metal are used as an additive in solid-state lasers based on YAG, Yttrium aluminum garnet. The beauty of these infrared lasers is that their radiation is well absorbed by water, which makes up about 70% of the human body. Thus, with the help of the erbium laser, you can easily and almost painlessly perform surgeries or remove skin growths. And because such a laser has a wavelength, at just 3 micrometers, you can avoid damaging the surrounding tissues with thermal radiation. So today, you can't do without rare earth metals if you want. For example, to quickly and without side effects remove a wart from your face. Another rare earth metal, thulium, is also used today in lasers based on YAG, Yttrium aluminum garnet, only in a mixture with chromium and holmium. These infrared lasers are mainly used today in the military or in meteorology. In addition to this, thulium, along with erbium, is added to fiber optic signal amplifiers that boost the infrared signal in those underwater cables all around the world. Without them, the infrared signal would weaken and be lost due to gradual absorption, even by the best fiber optics made from metal fluorides. Well, the last 2 rare earth metals, besides their low abundance and high price, also have quite rare applications, which are nevertheless quite interesting. For example, both terbium and its compounds, along with thulium and erbium, are used as additives in optical glass, and they are also applied in medicine. But the most interesting thing in this area today, in my opinion, is the metal lutetium, or more precisely its isotope lutetium-177. Today, this isotope. Obtained in nuclear reactors, it's used to treat quite rare types of cancer, specifically for treating neuroendocrine tumors. Interestingly, one dose of such a drug containing lutetium-177, called Lutathera, costs about 20,000 euros. And the entire treatment course involves administering 3 doses of this medication. So this thing is quite expensive. Besides that, it's already stable. Isotope, lutetium they are already used together with yttrium in unusual scintillator crystals. These crystals can effectively convert invisible X-rays into light, which is why they are widely used in computed tomography. Well, I think after watching this video, you learned more about these unusual rare earth metals, and why now, and in the future, they will play a more important role in industry and various sectors. Well, if you liked this video, as always, don't forget to give it a thumbs up and subscribe to the channel, where you'll learn a lot more new and interesting things.